Welcome, my friends. Consider the sequence 2, 10, 50, 250, ... Each term in the sequence is 5 times the previous term, as 2 times 5 is 10, 10 times 5 is 50, and 50 times 5 is 250. And the ... indicates that the sequence goes on forever, to infinity. In general, a geometric sequence is a sequence in which each term can be found by multiplying the preceding term by the same value. The explicit formula for a geometric sequence, which can be used to find any value in the sequence without needing to know the previous value, is a sub n is equal to a sub 1 times r to the n minus 1 power, where a sub n is the nth term in the sequence, a sub 1 is the first term in the sequence, r is the common ratio between successive terms, and n is the number of the term you want to find, which will be a variable in the formula. In our example, a sub 1 is equal to 2, as 2 is the first term, and r is equal to 5, as we must multiply each term by 5 to get the next term. Plugging into the formula, we have a sub n is equal to 2 times 5 to the n minus 1 power. We can use this formula to find whichever term that we want. So a sub 10, which is the 10th term, could be found by plugging in 10 for n. We have a sub 10 is equal to 2 times 5 to the 10 minus 1 power, which is 2 times 5 to the 9th power. If you plug this into your calculator, you should get 3,906,250. So you can see how quickly geometric sequences can grow if the value for r is even as small as 5. Here is another geometric sequence. 200, 100, 50, 25, ... and we want to find the 10th term. This sequence is a geometric sequence as the common ratio between terms is 1/2. Each term is 1/2 as large as the previous, so r is equal to 1/2. The first term is a sub 1 is equal to 200. The explicit formula for this geometric sequence is a sub n is equal to 200 times 1/2 to the n minus 1 power. We can plug in 10 for n to find the 10th term. We have a sub 10 is equal to 200 times 1/2 to the 10 minus 1 power, which is 200 times 1/2 to the 9th power. 2 to the 9th power is 512, so we have 200 times 1 over 512. This simplifies to 25 over 64, so the 10th term in the sequence is 25 over 64. How about this one? 6, negative 15.6, 40.56, negative 105.456, ... Is this a geometric sequence? And if so, can we find an explicit formula? It looks like this might be geometric, but it isn't clear. If we take negative 15.6 and divide by 6, we get negative 2.6. If we take 40.56 and divide by negative 15.6, we also get negative 2.6. Negative 105.456 divided by 40.56 is also negative 2.6, so it appears that this is a geometric sequence with a common ratio of negative 2.6. The next term in the list can be found by multiplying the previous term by negative 2.6. So that means r is equal to negative 2.6, and that the first term is a sub 1 is equal to 6. The explicit formula for this sequence is a sub n is equal to 6 times negative 2.6 to the n minus 1 power. Let's find the 20th term. We have a sub 20 is equal to 6 times negative 2.6 to the 20 minus 1 power, which is 6 times negative 2.6 to the 19th power, which is, if you plug it into your calculator, negative 459,880,359.1. This is the 20th term. Another interesting thing about this sequence, which you probably already noticed, is that it alternates from positive to positive back and forth every other term. We call sequences like this alternating sequences, which happen whenever the value for r is negative. Let's try this one. We want the 6th term of a geometric sequence that has a common ratio of 1/3 and a first term of 3. That means r equals 1/3 and a sub 1 is equal to 3. So the explicit formula is a sub n is equal to 3 times 1/3 to the n minus 1 power. Plugging in n equals 6, we have 3 times 1/3 to the 6 minus 1 power, which is 3 times 1/3 to the 5th power. This is the same thing as 3 over 3 to the 5th, which is 1 over 3 to the 4th. 3 to the 4th is 81. So our answer is 1 divided by 81. How about this one? A geometric sequence has a common ratio of r equals -5, and the 8th term is a sub 8 is equal to 41. Find the 12th term, a sub 12. Now, we don't have the first term, so we can't write an explicit formula. There are two ways to solve this. The first way, which is inefficient, is just to write out all of the terms between the 8th and 12th term. We would have a sub 8 is equal to 41, which was given, and then a sub 9, which is 41 times -5, since the common ratio is -5, which comes to -205. Then we have a sub 10 is equal to -205 times -5, which is positive 1025. Then we have a sub 11 is 1025 times -5, which equals -5125. And finally, a sub 12 is equal to -5125 times -5, which is 25,625. The 12th term in the sequence is 25,625. This process works, but is inefficient, especially if I was to ask for something like the 100th term. A better way is to recognize that from a sub 8 to a sub 12, we had to multiply by the common ratio of -5 4 times. Once to get a sub 9, twice to get a sub 10, 3 times to get a sub 11, and 4 times to get a sub 12. So a shortcut is to take the difference in the subscripts and multiply by the ratio that many times. For us, we have 12 minus 8, which is 4. This is the number of times 41 needs to be multiplied by -5 to reach the 12th term. We have 41 times -5 times -5 times -5 times -5, which is the same thing as 41 times -5 to the 4th power, which again is 25,625. Let's try another one. If r is equal to 3 in a geometric sequence, and the 7th term, a sub 7, is equal to 19, find the 23rd term. Well, there's no way I'm writing out all the terms between the 7th and 23rd term, so I'm going to use the shortcut. I have 23 minus 7, which is equal to 16, so I need to multiply 19 by the ratio of 3 16 times. I have 19 times 3 to the 16th power, which is equal to 817,887,699. This is the 23rd term in this sequence. What if r is equal to 2 in a geometric sequence, and the 15th term is a sub 15 is equal to -208? Find the 11th term. This one is a little different, since we have a later term, the 15th term, and want to go backwards to find the 11th term. The common ratio is 2, so we have to multiply by 2 to get the next term. But if we want to go backwards, we would have to multiply by the reciprocal of 2, which is 1/2. Let's find the difference in subscripts. We have 15 minus 11, which is equal to 4. So we need to multiply by not 2, but instead 1/2 4 times. We have -208 times 1/2 to the 4th power, which is -13. The 11th term is -13. Now, sometimes you might be interested in summing a sequence, what is technically called a series. So if, instead of commas separating the values in your sequence, you have plus signs, then you have a series. Take, for example, 3 plus 6 plus 12 plus 24 plus 48 plus ... Say that we want to sum the first 5 terms, which I have shown here. Obviously, you could just plug them into your calculator, but that isn't going to work so well if I ask you to sum the first 500 terms, so we would like a nicer formula. I'm not going to prove it to you, but it turns out that the sum of a geometric sequence can be found by s sub n is equal to a sub 1 times 1 minus r to the nth power divided by 1 minus r, where s sub n stands for the sum of the first n terms, n is the number of terms that you want to sum, a sub 1 is the first term, and r is the common ratio between terms. If we want to sum the first 5 terms, a sub 1 is the first term of 3, r is equal to the common ratio of 2, and n is the 5 terms that we want to sum. Plugging in, we have s sub 5 is equal to 3 times 1 minus 2 to the 5th power divided by 1 minus 2, which is equal to 3 times 1 minus 32 divided by 1 minus 2, or 3 times -31 divided by -1, which is -93 divided by -1, or 93. This is the same thing as 3 plus 6 plus 12 plus 24 plus 48, which is also equal to 93. Take a look at this one. 2 plus negative 10 plus 50 plus negative 250 plus ... The common ratio is r is equal to negative 5, and the first term is a sub 1 is equal to 2. We want to sum the first 8 terms, which means n is equal to 8. Plugging into the formula, we have a sub 8 is equal to 2 times 1 minus negative 5 to the 8th power divided by 1 minus 5. Be very careful to put parentheses around the value for r if r is negative or a fraction. This simplifies to 2 times 1 minus 390,625 divided by negative 4, or 2 times negative 390,624 divided by negative 4. Typing this into your calculator, you should get 195,312, which is the sum of the first 8 terms. Let's try this one with summation notation. We want to find the sum from k is equal to 1 to 9 of 1/3 to the kth power. This tells us to plug in k equals 1, and then add to that the value we get when we plug in k equals 2, and then add to that what you get from k equals 3, etc., all the way through k equals 9. If you plug in k equals 1, you get 1/3 to the first power, which is 1/3. For k equals 2, you get 1/3 to the second power, which is 1/9. For k equals 3, you get 1/3 to the third power, which is 1/27. You can hopefully verify that the common ratio is 1/3, as each term can be multiplied by 1/3 to get the next one. So r is equal to 1/3, and the first term is also a sub 1 is equal to 1/3. There are 9 terms in the sum, so n is equal to 9. Plugging into the formula, we have s sub 9 is equal to 1/3 times 1 minus 1/3 to the 9th power divided by 1 minus 1/3. This simplifies to 1/3 times 1 minus 1 over 19,683 divided by 2/3. This is 1/3 times 19,682 divided by 19,683 divided by 2/3. This simplifies to 19,682 divided by 59,049 divided by 2/3. This is the same thing as 19,682 divided by 59,049 times 3/2, which is 59,046 divided by 118,098. It turns out both the numerator and denominator can be divided by 6 to reduce this fraction to 9,841 divided by 19,683, which is very close to 0.5. This is the sum of the first 9 terms. Okay, the last thing to discuss is the sum of an infinite geometric sequence. It may seem counterintuitive, but under certain circumstances, an infinite geometric sequence actually has a sum. Consider this geometric sequence. We have 2, 4, 8, 16, 32, ... on and on forever. This is an infinite geometric sequence because it goes on forever, indicated by the ... There is no sum of this infinite sequence because the terms diverge. They get bigger and bigger and bigger and approach positive infinity. You could find a partial sum, say of the first 20 or 30 terms or whatever you want, but there will be no sum of all of the terms as the sequence diverges to infinity. On the other hand, consider this sequence: 1/2, 1/4, 1/8, 1/16, ... This is an infinite geometric sequence, but the terms do not approach infinity. They actually approach 0. They are getting smaller and smaller and smaller. By the time you get to, say, the 100th term, the value of the terms will be extremely close to 0. It turns out a sequence like this actually does have a sum. You can imagine what the formula will be by considering the sum of a finite geometric sequence, which is s sub n is equal to a sub 1 times 1 minus r to the nth power divided by 1 minus r. If the sequence is infinite, then you are plugging in extremely large values for n. If you plug in a super large value for n, and r is a fraction, like 1/2, you are going to get a fraction, less than 1, raised to a huge power on this term. Fractions raised to really, really big powers get really, really small. So as you approach infinity, the r to the nth term will disappear, and you will be left with s sub n is equal to a sub 1 times 1 divided by 1 minus r, or simply s sub n is equal to a sub 1 divided by 1 minus r. Since the nth term doesn't apply anymore since n approaches infinity, we write the formula as s is equal to a sub 1 divided by 1 minus r, without the subscript n. This is the formula for the sum of an infinite geometric sequence. take the first term, a sub 1, and divide by 1 minus the common ratio, r. There is one condition though. This only works if r is between -1 and 1. If r is 1 or larger, or -1 or smaller, the series diverges to positive or negative infinity, and there is no infinite sum. The finite sum also has a restriction on r, which I didn't mention before. R can't equal 1, as then you would have the divide by 0 error. But in that case, you kind of have a boring sequence because every term will be exactly the same, and you don't really need a sum formula to find the sum. Anyways, let's apply the infinite sum formula to our problem. We have a common ratio of r is equal to 1/2, and also have a first term of a sub 1 is equal to 1/2. So the infinite sum is s is equal to 1/2 divided by 1 minus 1/2, which is just 1/2 over 1/2, or simply 1. If you add up all of the terms in this infinite sequence, you actually get a value, and that value is 1. Very interesting. Let's try another one. We have 2 minus 3/2 plus 9/8 plus ... which we would like to sum if possible. Is this a geometric series? Let's find out by dividing a few numbers. -3/2 divided by 2 is the same thing as -3/2 times 1/2, which is -3/4. 9/8 divided by -3/2 is the same thing as multiplying by the reciprocal of -2/3, which is -18 over 24, which simplifies to -3/4. It appears that this is a geometric series with a common ratio of r is equal to -3/4. The first term is a sub 1 is equal to 2. Therefore, the infinite sum is s is equal to 2 divided by 1 minus -3/4, which is 2 divided by 7/4. Divided by 7/4 is the same thing as multiplying by the reciprocal of 4/7. So we have 2 times 4/7, which is equal to 8/7. The sum of this infinite geometric series is 8/7. Let's try one with summation notation. We have the sum from k equals 1 to infinity of 5 times 1/5 to the kth power. This tells us to plug in k equals 1, and then add to that the value you get when you plug in k equals 2, continuing forever and ever. Since each number will get smaller, as we have a fraction raised to larger and larger powers, the series will approach 0, and there will be an infinite sum. If we plug in k equals 1, we get a sub 1 is equal to 5 times 1/5 to the first power, which is 5 times 1/5, or just 1. Then each term will be 1/5 of the previous, so that we have a sub 2 is equal to 5 times 1/5 to the second power, which is 5 over 25, or 1/5. Hopefully you can see that the common ratio is r is equal to 1/5, and the first term is a sub 1 is equal to 1. Plugging into the formula, we have s is equal to 1 divided by 1 minus 1/5, which is 1 over 4/5, or 5/4. If you add up all the terms in this sum to infinity, you will get 5/4. Alright, my friends, that completes our discussion of geometric sequences and series.